Okay, this is the homework. This is lesson 8A, part 2. We're about to start. Okay, so this is the formula for chi-squared. So this is the test statistic. Do you remember, like, we've called test statistic different names? I think our first test statistic was Z, and then T, and now we have chi-squared. So you kind of do it's kind of like a cursive, I don't know how to explain it. So it's kind of a funny looking X there, but it's called chi-squared. It's the sum of the observed minus expected squared on top divided by expected. And that's the formula we use if we want to get it by hand. Make sure to use observed and expected counts, not the proportion. So what that's saying is don't put decimals there. Like this is observed counts. Now they can be decimals, but not like percentages, right? These are counts. And this is on the formula sheet. You don't have to memorize that formula. So chi-squared distribution is described by a density curve that only takes non-negative values, and it's always, always, always skewed right. So these are 3 pictures of a chi-squared test. Technically, degrees of freedom 1, which we hardly ever see, would be just straight skewed right. Like it doesn't even come down on the left-hand side. Typically, if I'm drawing a chi-squared graph, I just kind of draw something skewed right. You know, that's how I draw. The more skewed is a smaller value. So as it does get degrees of freedom a little bit higher, it gets a little bit more symmetric. They're talking about from the table. We don't do that. We can find the value of this. So let's say we wanted to find this value. So let's get our calculator out. And let's go to find chi-squared CDF. So see if we can do this. So I'm pretty sure it's under menu 6. I'm guessing it's a distribution, chi-squared CDF. So lower bound 9.8, upper bound infinity or a big number. Degrees of freedom. It's the number of categories minus 1. And so evidently this one, it's 5. And you get 0.0811. Yeah, the table doesn't give you always super accurate results. The calculator does. You get 0.0811. Okay. So the null is correct. Complete the chi-squared statistic there. Find the p-value by calculating the probability of getting chi-squared or larger with that same degrees of freedom. So going back to this one, let's try to set this up. So I'm just going to try to do this one by hand. Let's see if we kind of can. Sorry, move it over. Okay, so observed count. So it's going to chi-squared is going to equal the observed, so in the numerator, so that's 32 minus 20 squared over the expected value, which is 20. That's for the first term. That's January through March plus, this would be what? Weird, 20 minus 20 squared, which is 0 over 20. Plus, I'm putting this down below, but it's all in line there. So that would be observed would be 16 minus 20 squared, so that would become positive over 20 plus 12 minus 20. Again, negative, it can become positive when you square it over 20. And that should give you your expected value if you wanted to do it by hand. We don't often have to do that, but you want to be able to set that up. By the way, it is okay to skip one of those and just put ... in between those. If there's a whole lot of them, skip one of them, skip some of them. Just do first and last, maybe the second one, and make sure they know you know what you're doing when you do this. If you type those in your calculator separately, those fractions, you would get those 4 numbers. and then you add them up to get 11.2. That's pretty big. See if that's big enough or not to reject, see what our decision will be. Find the p-value. So if our chi-squared value is 11.2, so let me just kind of, this is weird to draw. How do I draw that? So I might have to redo this because I think I used to know a little trick on this one, but I may have forgotten it. So I want to see something, see if they drew it. See if I can remember my trick. So degrees of freedom is number of categories minus 1. There's 4 different quarters there, so it's going to be 3. So I think this is right. I think maybe that's where the peak is at degrees of freedom. I forget. I used to know a little trick about this, but I'm guessing 3 somewhere around there. But 11.2 is way out there, so we're shading this way, right? So that's our curve. And so to find the p-value, you can do chi-squared CDF. So let's try that. So we go chi-squared CDF. So menu, again, 6.5, there it is, if you look for it. Lower bound is 11.2, that's our chi-squared value. Upper bound is infinity. Degrees of freedom is just 3, number of categories minus 1. We get 0.017, 0.0107, sorry, 0.0107. And there it is. And so that p-value is less than, evidently 2.5% was our cutoff there. Did it say that? Wonder if it said the alpha level. I don't think it said that. I don't know where they got that from. That's less than, in terms of p-value. So it must have been 2.5% somehow. So assuming the population of NHL players born in each quarter are the same, there's a 0.0107 probability getting distribution of birthdays, a random sample size of 80, this different or more different than the hypothesized distribution by chance alone. So that's interpreting of the p-value, not the actual test. You're not concluding in the test. So assuming the null is true, right? Assuming there is, the null is true. That's what that is. Oh, you can do the whole test in your calculator, right? So what you have to do is you have to call your list names here appropriately. So this would be, go to data statistics. You can call it observed and expect. Don't use exp. Expect's okay, but exp is some kind of command of some kind, so don't do that. 32, 20, 16, 12. Expected values are 20, 20, 20, and 20. Make sure you press enter, get out of that last term. I like to add a calculator page. So let's see where it is. Menu 6, got to be 7 where the tests are, and there's a chi-squared GOF, that stands for goodness of fit. And so the observed list, oh, so nice to just say observed. Expected. Degrees of freedom is number of categories 4 minus 1 is 3. Should do the whole thing for us. So you have to show the p-value and the chi-squared value. I also recommend highly the degrees of freedom. Comp list, I'm just going to show you that. Comp list is, let's see if you scroll down to stat comp list, there it is. It gives you those 4 values. Remember how they said they took each fraction and simplified it? They got 7.2, 0, 0.8, and 3.2. Remember back here, when we first started today, those 4 numbers there for chi-squared, 7.2, that's the first fraction, 0, second fraction, 0.8, and then 3.2. So you can do that to get those answers there if you want. Comp list shows you those 4 numbers. You can use a calculator to carry out the mechanics for the do section, right? But if you have some values incorrect, you don't get partial credit for that. So you use the calculator method. Be sure to include chi-squared, degrees of freedom, and p-value in the do-step. Those are the 3 things. That's what I've been telling you. I mean, the test statistic, which in this case is chi-squared. Now, the null hypothesis, it has a specified variable of interest. Okay, so let's try one more, and this is on your sheet if you have that in class. Many people love tree-lined streets, especially in big cities where tall buildings can dominate the landscape. Are trees in New York City streets proportionally distributed across the 5 boroughs? That is, if a borough has 30% of the land, does it also have 30% of the trees? How proportionally are the trees handed out there compared to the land? So this table shows the percentage of the area that is dedicated to trees and the actual area that is trees there. And it gives you the number of trees in each branch. So those are the observed number from a sample of 1,000 trees. And these are the areas of that. So, first, what's the null? Null is there's no difference. There's nothing going on here, right? The percentages are all what we expect them to be based off the area percentages, are proportionally distributed. Trees in New York City are not proportionally distributed. So the alternate is always just not the hypothesis in this type of test. So they didn't give us one, so we're going to say 5%. You can also write it with numbers, but very few students will do that. Chi-square test for goodness of fit is the name of it. Random sample of trees. Thousands, less than 10% of all trees in New York City. All those are true. Expected counts are 140.4. So how did they get those? So just want to make sure you understand that. So to get one of those expected counts, you take the percentage, like for the Bronx, the percentage is, well, it's n, which is 1,000. There's 1,000 trees. That was our n, times, I'm going to say 0.1404. Because the way they wrote it as a percentage. So I think that's right. Oh, wait, what did I say? I think it should be times there. 140.4. So our first one's 140.4, and then we're going to do 1,000 times 0.2309. That gives us 30.9, etc. We're going to keep going with that and get all of our expected values. So I don't think they wrote them down, but then they plugged those expected values into the observed minus expected. We got the first two there, 140.4 and 230.9. Just plug them all in. If those middle two, you want to kind of like put ... there, that's totally fine. You don't have to show all that work. Again, you don't even have to show any of that work necessarily. I want you to know how it works for the multiple choice, but you get those right without doing that. You can save some time writing out the first two terms and then using an ellipse or ellipses. Yeah, so they mentioned that you can do that. You're allowed to. Degrees of freedom is number of categories. There's 5 boroughs, minus 1 is 4. Okay, I think the formula is, when you're drawing this, so degrees of freedom was 4. I think it's that minus 1 is the peak. That sounds about right. It looks like 2 or 3 is the peak. I don't know if that's the rule. I'm trying to remember my rule of that one. So you could chi-square this guy, right? Get if you do that in your calculator, let me just show you what you do. Oops, sorry, wrong calculator. So if you go to chi-squared menu 6.5 chi-squared CDF, so 15.44, it's always right skewed, so it's always going to go that way. 9 degrees of freedom, I think, was 5 minus 1 is 4. You get the 0.00387. Because our p-value is much smaller than 0.05, we reject the null. We have convincing evidence that the trees on New York streets are not proportionally distributed across the 5 boroughs. So they're not because we've got such a small p-value. Because we rejected, the only one we could have done is a type 1 error, right? That means we found convincing evidence trees in New York are not proportionally distributed, but guess what? They are. That's your lesson for today. If you're in class, we might have an activity following this. I'm not sure, but that's your lesson for today.